Anaerobic digestion feedstocks. In this segment, we are going to discuss about different conventional and emerging feedstocks suitable for anaerobic digestion, feedstocks energy value, co-digestion, and feedstocks biochemical methane potential. Let's discuss about conventional and emerging feedstocks. Traditionally, manure, animal waste, and wastewater sludge were the main feedstocks for anaerobic digester. But recently, food processing waste and organic waste from household have drawn significant attention as promising feedstock, as they can increase gas production significantly. In addition, agricultural residues, yard waste, and even municipal solid waste can be used as feedstock for anaerobic digestion after appropriate pretreatments. New pretreatment technologies and innovative digester types have opened the option of recovering energy from diverse waste streams rather than sending them to landfill. Anaerobic digestion feedstocks can be grouped based on their sources. So from agricultural and farm side, we have harvest remains, energy crops like corn, Sudan grass, maize, millet, white sweet clover, etc. Algal biomass, that's an emerging feedstock. And also we have manure from pig, cow, and poultry. Those are used traditionally over the years. Also from municipal side, we have source separated organics from municipal, like fruit and vegetable waste, food waste, coffee and tea filters, and other organic leftovers. Also we have yard or garden waste like leaves, plants, vegetables, branches and tree trimmings, grass clipping, etc. And sewage sludge has been conventional, one of the conventional feedstocks. Also we have municipal solid waste. From industrial side, we have different industrial waste like food and beverage processing industry waste, dairy industry waste, starch industry waste, sugar industry waste, as well as slaughterhouse waste. Feedstocks energy value. Different feedstocks have different methane production potential or different energy recovery value. Anaerobic digestion process was originally designed for manures and sewage sludge, but those two feedstocks do not have much energy value left as they have already gone through some digestion inside the animal's body. In general, the feedstocks of high organic content that is easily degraded by anaerobic bacteria are considered good feedstock for anaerobic digestion, such as food and food processing waste, fats, oil, and fat, etc. Some energy crops also have high biogas production potential, such as corn, maize, and grass silage. Poor candidates for anaerobic digestion are yard waste, woody waste, etc. As most anaerobes are unable to degrade lignin, the major fraction of this waste. So here is the energy value profile of different anaerobic digestion feedstocks. As we can see, at the top we have glycerin, fog, food waste, biosolid, and at the bottom we have crop residuals, dairy manure, and hog manures. What is co-digestion? Traditionally, manure, animal waste, and wastewater sludge were the main feedstocks for anaerobic digester. But manures and sewage sludge are not the best quality feedstocks as they had already gone through a digestion process. So in order to enhance the gas production, focus has been shifted to high energy feedstock that can be blended with manure or sewage sludge and digest together. This process of blending or digesting two or more feedstock at the same time in an anaerobic digestion process is known as co-digestion. The most common situation of co-digestion is a higher amount of basic feedstock like sewage sludge or manure with a lower amount of high-strength organic waste like fog, food waste, corn silage, slaughterhouse waste, organic fraction of household waste, etc. can be added to the digester together for a higher biogas yield. Food waste is considered as one of the high energy value co-digestion waste because food waste has 3 times higher methane production potential when compared to biosolid and also much higher biodegradability than biosolid. It means even when a higher amount of food waste is added to the digester as a feedstock, the final residue will only increase by a smaller amount, but the gas production will increase significantly. The food waste or organic waste can be combined waste collected from various places like restaurants, school cafeterias, vegetable markets, fish markets, household kitchen waste, and food leftovers. Rather than sending this energy-rich waste to landfill, they can be co-digested and converted to energy. So many high-strength and emerging feedstocks have the potential to be a co-digestion feedstock. A good co-digestion feedstock should fulfill certain requirements, and they are: it should be easily biodegradable with a high biogas production potential. It should not contain any inhibitory substances for the process. It should have macro and micronutrients that may enrich the primary feedstocks. It should be available in sufficient quantities and at a reasonable price in the local market. And it should have an easy reception and storage option in the plant. So some example of co-digestion waste are fat, oil, and grease, known as FOG, can be collected from these traps. Source-separated organics, restaurant food scraps, food manufacturing and baking industry waste, breweries, distilleries, slaughterhouse waste, and dairy waste. What are the benefits of co-digestion? First of all, renewable energy generation. Co-digestion of food waste and organic waste allows increased biogas production that can be utilized in the plant itself and also can be sold to the grid when in excess. Greenhouse gas reduction. When food waste or organic fraction of municipal solid waste are dumped in landfill, they generate a large amount of methane. But if co-digested, almost 3 times higher methane production can be achieved compared to biosolid. Waste to energy. Utilization of food waste and OFMSW as anaerobic digestion feedstocks not only minimizes waste stream but also allow the recovery of valuable energy and resources. Cost recovery. The anaerobic digestion plant can recover some of its operational cost from the enhanced gas production or on-site power generation. So let's discuss about feedstocks biogas potential or BMP assay. Biogas generating potential of any feedstock or feedstock blend can be predicted through a lab-based approach, and that is commonly known as biochemical methane potential assay or BMP assay. In general, the BMP assay is conducted by combining a single feedstock or feedstock blends, inoculums, and stock solution in a closed bottle in a batch mode. Inoculums are an active anaerobic culture added to the bottle to reduce any lag time. Stock solution are a mixture of macronutrients, micronutrients, and vitamins to assure that biogas production are not limited during the assay. A water bath can be used for temperature control and a shaker can be used for mixing the solution. BMP assay can be continued for as long as 60 days and biogas produced can be measured periodically or continuously. A control solution bottle containing inoculums and stock solution should also be used to determine gas production from the inoculums alone. BMP assay should always be conducted in application to assure the repeatability of the test result. So following parameters are usually analyzed in a BMP assay, that is before and after feedstock's characteristic. The feedstock characteristics like pH, chemical oxygen demand, total solids, and volatile solids are checked before and after the BMP assay. The before assay result help to determine the feedstock's quantity required for maintaining the assay for as long as 30 to 60 days. The after assay feedstock characteristics reveal organic material destruction and biodegradability of the feedstock during the assay, and also the total biogas production and gas composition. Total gas production can be measured during the BMP test either by collecting it manually or by continuously using commercially available gas meters and software. Later, biogas composition can be analyzed by a gas chromatograph. In this slide, I have listed some of the references for conducting and optimizing BMP assay, so you can refer to them while conducting an assay. And with this slide, I'm going to close this segment and we'll continue in the next segment that is about feedstock pretreatment for anaerobic digestion.